On this part, we're going to talk how to estimate the logistic model and how to use the logistic model for classification. Unlike in linear regression, where there exists a closed-form solution to finding the estimates of beta that minimize the loss function, logistic regression estimates cannot be calculated through a simple matrix multiplications. Some reminders from before. In linear regression, what loss function we use to determine the parameter estimate, MSE, and what was the probabilistic perspective on linear regression, normal distribution. Logistic regression also has a likelihood or probabilistic-based approach to estimate parameter coefficients. Now, logistic regression tells us the probability of getting 1 or 0 given x. For any x, the probability of getting 0 or 1, heads or tails, is given by the logistic function shown in the plot with an orange line. So at any given x, there's a probability of y is equal to 1, which is given by p from the orange line. And the probability of y is equal to 0 is 1 minus p. We can write that in a closed form. The probability of y is equal to any y, 0, 1, is the probability at that given point p to the power y, where y is 0 and 1, times 1 minus p to the power 1 minus y. The likelihood then of a single observation is given by the same formula, p to the y times 1 minus p, 1 minus y. And assuming the observations are independent, the total probability or likelihood of getting a certain outcome will be the product of all individual probabilities. So be the product of p to the y, 1 minus p to 1 minus y. Now the best model is the model that gives us the highest probability. We can adjust the betas such as we get the maximum probability given our data. We usually do not like to deal with products, the capital P you see in the formula. So with a little bit of algebra, we can show that finding the maximum probability given the data is identical to finding the minimum of the negative log of the probability, or minimizing the negative log likelihood. We can write that new loss function, which is the negative log likelihood, to be the negative of the sum of y log p plus 1 minus y times log 1 minus p. This loss function that we use for logistic regression is also known as the binary cross entropy. We can write this loss function, the binary cross entropy, in its full glory for logistic regression as the negative of the sum of y log of p, but now p is given by the logistic function, which is 1 over 1 plus exponential of negative beta x1 plus 1 minus y, and the log of 1 minus 1 over 1 plus exponential of minus beta x1. And then we minimize that. But how do we minimize this with respect to the betas? Well, we know how to do it. We differentiate with respect to betas, we equate that to 0, and solve for it. Easier said than done. We know that it does not have a closed form solution. So what do? We use iterative methods such as gradient descent or Newton's method. Once we do that, we have our estimates for our model. Let's go to our example of the heart data. And here we like to predict whether or not a person has a heart disease. And we like to make this prediction for now just based on the maximum heart rate. So the data are given with the green dots, and the estimate of the model after we minimize the negative log likelihood or the cross entropy will be the orange line. And if we want to make classification, we've done what we have said before. Any individual with a probability higher than 0.5, we're going to predict that he has a heart disease. And any individual with a probability of having heart disease less than 0.5, you get the good news, no heart disease.